Welcome to the TOEFL Listening section. In this part, you will hear one or more conversations in an academic or campus context, such as a discussion between a student and a professor, or between two students. You may take notes while listening. Listen to part of a conversation. You will hear it only once, so listen carefully. After the conversation, you will answer questions about what you heard. Some questions will ask you about main ideas and details. Others will ask about implied meaning, speaker attitude, or how ideas relate to one another. Use both what is stated and what is implied to answer.
Good afternoon, Dr. Carter. I wanted to go over adaptive optics in telescopes before my presentation tomorrow.
Hello, Emily. That is a great topic. Where would you like to start, the basic principle or specific instruments?
Maybe the principle first. I understand atmospheric turbulence blurs images. How exactly does adaptive optics correct that?
In simple terms, adaptive optics measures the distorted incoming wavefront, and then applies an opposite deformation to a mirror to cancel the errors in real time.
So we need a sensor to measure the wavefront. Is that where a Shack-Hartmann sensor comes in?
Exactly. A Shack-Hartmann sensor samples the incoming wavefront with a lenslet array, and measures local slopes by tracking spot displacements on a detector.
And the deformable mirror has actuators that move to correct those slopes.
Yes, the deformable mirror contains many actuators. The actuator density and the influence function of each actuator determine how finely you can shape the mirror surface.
I read about closed-loop control in AO systems. How fast does that loop need to run?
The loop must run faster than the Greenwood frequency, which characterizes the temporal variations of turbulence. On a good night for near-infrared work, that might be a few hundred hertz.
That seems fast. Does latency matter a lot?
Latency is critical. Any delay between sensing and mirror correction results in residual wavefront error. Minimizing latency improves Strecal ratio and image contrast.
Speaking of Strecal ratio, how much improvement can adaptive optics provide?
It depends on wavelength and system. In the near-infrared, a good AO system can raise the Strecal ratio from around 0.1 without correction, to over 0.5, or even 0.8, with extreme adaptive optics under excellent conditions.
What is extreme adaptive optics?
Extreme adaptive optics, or XAO, uses very high actuator counts and very fast control, to achieve very high Strecal ratios and contrast. Instruments like Sphere at the VLT, and GPI at Gemini, use XAO to directly image exoplanets.
I was hoping to include real telescope examples. Could I mention Keck and the VLT using laser guide stars?
Yes, Keck uses laser guide star adaptive optics regularly. The VLT also uses laser guide stars for instruments like Sphere. Laser guide stars create an artificial beacon in the sodium layer to measure turbulence where a bright natural star is not available.
Are there drawbacks to laser guide stars?
There are. A laser guide star cannot measure overall tip and tilt accurately because it is created in the atmosphere and shares the same motion as the turbulence along the beam path. So a nearby natural guide star is still needed for tip tilt, or you must use multiple techniques to recover that information.
You mentioned multiple techniques. Does that include tomography and multi-conjugate adaptive optics?
Yes. Multi-conjugate adaptive optics, or MCAO, uses several deformable mirrors conjugated to different altitudes and multiple guide stars to correct turbulence over a wider field of view. Tomography reconstructs the three-dimensional turbulence profile from several guide stars.
So MCAO improves image quality across a larger field than a single conjugate system.
Correct. Single conjugate adaptive optics corrects well near the guide star, but performance falls off with angular separation due to anisoplanetism. MCAO aims to keep correction uniform over a larger area.
How do observatories decide between putting actuators on a small deformable mirror or using an adaptive secondary mirror?
Adaptive secondary mirrors replace a conventional secondary with a deformable mirror. They reduce the number of warm optics and improve throughput. However, they are technically challenging to build and maintain. The choice depends on telescope design and science goals.
What about calibration and non-common path errors between the wavefront sensor and science camera?
Calibration is essential. Non-common path aberrations arise because the wavefront sensor and science path see slightly different optics. Instruments use internal calibration sources, phase diversity, and focal plane wavefront sensing to measure and correct those residuals.
Can adaptive optics be applied to large future telescopes like the IELTS?
Absolutely. Extremely large telescopes will rely heavily on adaptive optics. The IELTS will use multiple deformable mirrors and a complex laser guide star constellation to meet diffraction-limited performance in the infrared and improve performance in the visible.
Are there any current research challenges in adaptive optics I could highlight?
Yes. Challenges include reducing latency, improving wavefront sensors such as pyramid sensors for higher sensitivity, managing laser guide star elongation in very large telescopes, and developing predictive control to compensate for temporal delays.
That is helpful. For my conclusion, I want to state the main benefit in one sentence. How about this? Adaptive optics restores diffraction-limited resolution by sensing and correcting wavefront distortions in real time.
That is a clear summary. You might add a short example. Say it enables direct imaging of exoplanets by increasing strial ratio and contrast.
Great, I will add that and mention Keck and sphere as examples. Thank you for the guidance.
You are welcome. Good luck with your presentation and let me know if you want feedback on your slides.
Listen again to part of the conversation. Then answer the question.
We use closed-loop control to drive the deformable mirror, based on wavefront sensor measurements to reduce residual wavefront error.
This concludes the conversation portion. For more TOEFL practice tests and study materials, visit Spinta.org.